So this is a quick video for AQA Physics A-level students on the stability of the atom. Now this is mainly paper 1 content, however it could link into the nuclear physics topic in paper 2, and even it could potentially come up in paper 3. However, the paper 3 content will probably be more centered around the paper 2. So I'm mainly going to be focusing on the paper 2 content here, but it's good to just be aware that this is something that could come up on paper 2 because it has done in previous years. Now, the strong nuclear force is a force that counteracts the electrostatic force of repulsion between protons in the nucleus. Now, this force only affects nucleons, so protons and neutrons. It doesn't affect electrons at all. However, there are specific properties of this force. So this is a graph you 100% need to know for your exam. So the strong nuclear force has different characteristics depending on the distance between the protons in the nucleus. So below 0.5 femtometers, a femtometer is 1 × 10⁻10 meters, the force is repulsive. Now this is so that the protons don't become so attracted to each other that they collapse in and the nucleus collapse in on itself. Now, between 0.5 femtometers and 3 femtometers, the force is attractive, which will counteract the electrostatic force of repulsion. Now this is the typical distance between protons in the nucleus. So above 3 femtometers, the force is negligible. Otherwise, the protons would just be constantly attracted to each other no matter the distance. So above 3 femtometers, there's really no nuclear force existing. Unstable nuclei either have too many protons, neutrons, or both. Now, an unstable nuclei will always decay so that it becomes stable. Now, in nucleon-rich atoms, it will undergo alpha decay, and this is the equation for alpha decay, which you have seen at GCSE. Whereas for neutron-rich atoms, the atom will undergo beta minus decay, and this is something you've already seen at GCSE. However, it will also produce an anti-electron neutrino. This is something that's very important for conservation laws, which will be discussed in another video. Now obviously there's beta plus decay, which is very similar to beta minus. However, it is a proton decaying into a neutron. Now, a bit of history that you may need to know for the exam is that initially scientists believed that only electron was released in beta decay. However, energy was not conserved, so another particle had to carry away this energy, and that is the electron antineutrino. Now there's other reasons why. There's reasons why it must be an antineutrino and not a neutrino. Again, we'll discuss that in another video when I go through conservation laws, but for now, this is what you need to know. There are other ways that the atom may change its state. This is through electron capture and through gamma emission. Now this is also caused by unstable nuclei. However, I'll make a later video on that because it goes into more in-depth knowledge about unstable nuclei. The reason that heavy nuclei, which are large, they have too many protons, neutrons, or both, decay is to do with the strong nuclear force. For example, let's take uranium-238. In uranium-238, not only is there too many protons, but there's also too many neutrons. Now, if there's too many protons, the strong nuclear force cannot fully cancel out the electrostatic force of repulsion because it will be stronger. If the nucleus is so large that there's too many protons and neutrons, the protons at the end of the nucleus will not feel the same strong nuclear force. As we can see from this graph, the attractiveness falls away as the distance from the center of the nucleus increases. The strong nuclear force is not the only thing that keeps atoms together. The number of neutrons there are in an atom can also dictate how stable it is. So neutrons will decrease the electrostatic force of repulsion between the protons as the distance between each proton will be larger. The number of neutrons along with the strong nuclear force will keep the atom stable. Now in paper 2 you talk about the AZ graph, which is not on paper 1 at all. It may be on paper 3, but I'll discuss that in another video which shows which atoms decay and what type of decay they decay by. So that's pretty much it for this video. There is more information on decay, however you need to know a bit more content in order to understand that. So I'm going to make a separate video and more videos on the whole particle physics chapter as a whole, and then eventually the nuclear physics chapter, so that I can explain decay in more detail. However, this is pretty much a lot of information that you need to know. This is the basics, and if you understand all this, then then you can pretty much smash a lot of questions. If you get a long answer question on how the nucleus is stable, you can talk about the strong nuclear force, you can talk about the electrostatic force, you can talk about the neutrons, then you can talk about decay. Pretty much everything here is very useful. This is the basics, this is what you need to know, but I will go into more in-depth knowledge in a later video. Thanks for watching.